Today we are going to be talking about another data structure called tries, and we are going to see its use in pattern matching. So I am going to be starting off with what are called standard tries, just the plain version of tries. Then we are going to move on to compressed tries. This is a space efficient way of keeping tries, and the last topic we are going to look at today is what are called suffix trees. Right? So the first two terms have tries in them, and the third has trees in them, and it's not a misspelling. Okay. So we recall in the last class we were looking at pattern matching. Given a piece of text, we were interested in matching patterns, finding out at what all places a certain pattern appears in the text. And what we had done there, if you recall, was that we had pre-processed the pattern. That is, we took the pattern, we computed this function, the failure function h on that pattern, and then we used that information to search for the pattern in the text. And the time we took was proportional to the size of the text. Yeah. So this preprocessing the pattern speeded up the time it took to match the pattern. If we did not compute the function, the failure function h, then we just had this brute force method of matching the pattern, which took order mn time, m the size of the text and n the size of the pattern. So after processing the pattern in time proportional to the length of the pattern, the Knuth-Morris-Pratt algorithm searches an arbitrary text in time proportional to the length of the text. Right? Now, if the text is very large, this is not a very good situation to have in. Right? So I have a very large piece of text which doesn't change, and I am searching for patterns in that text. So every time I search for a small pattern, if I am going to spend time proportional to the size of the text, that's a lot of time. Right. So you have some, let's say, collected works of Shakespeare in which you want to search for Veronica, and you are going to spend time proportional to the size of the text, which is very huge. Okay. So now what we want to do today is to process the text so that I can search for a pattern in time proportional to the length of the pattern. Okay. See, this becomes great because now patterns are typically very small, 7 characters, 15 characters, something like that, while your text could be 1,000,000 characters large. So you don't want to spend that much time every time you are searching for a text. But here today we are going to require that we will pre-process the text. We will work on the text initially, right, and we will have created some data structures on that, so that when a pattern comes, we can search for that pattern, all occurrences of that pattern we can spot in very little time, proportional to the length of the pattern itself, no matter what pattern comes. Right? In the previous, in KMP algorithm, it was the other way around. You processed the pattern, okay, you did a pre-processing on the pattern, so that no matter what text came, you could search on that text. Yeah, but there you were taking time proportional to the length of the text, therefore, which is quite expensive. Yeah. Okay. So we will come to this notion of tries today. So what is a try? I will perhaps show you a picture and I will explain it through this picture. So try is a data structure to maintain a set of strings. Okay. So let us say I have a set S of strings: beer, bell, bid, bull, buy, sell, stock, stop, let us say. Okay. This is an example I think I picked from Goodrich Samasya. Okay. Now I am going to create a tree here. Now this is not a binary tree, although no, it is clear that it is not a binary tree. In fact, the arity, the number of children that a particular node can have, can be as large as the size of the alphabet. Okay. We are working with the English alphabet, let us say here. So the size of the English, and let us say all our strings are lowercase characters. Okay. So the size of the alphabet is 26. So each node can have up to 26 children. Okay. Now the children of a node are ordered alphabetically. What does that mean? Okay, each node is going to have a particular character in it, and if I look at all the children of this particular node, then those are going to be ordered alphabetically, right? So B will precede C. If C were there, then C would come after B, and so on. So I have, this has just 2, B and S, so B comes to the left of S. This had 3, E, I and U, so they come one after the other in this order. So it's an ordered tree.
So the left to right notion of order is also maintained, of the order in the text, the alphabet, that is also maintained. So the left comes prior in the alphabet. That is maintained.
No, A comes before B, comes before C. That's all.
In the left to right.
Yeah, exactly. Yeah, so this is read left to right. It's English text and not Urdu or Arabic. Yeah. So we are going to, okay, now how is this organized? So look at, so suppose I were to start from here, right, and I were to follow a path in this tree. So suppose I came this way, B, E, A, R, beer. Beer is one of the words here. Okay. And suppose I were to take some other path, S, E, L, L, cell is another word here. Yeah, S, T, O, C, K, stock is another word here. So now you can build this thing. If I give you a set of words, can you build this try? Straightforward, right? What am I doing? At the very first level, I am looking at the first characters of all my words and seeing what are the various occurrences. If you look at the first character, I have just B's and S. So there will be one node corresponding to B and one corresponding to S. And within this B, so then this B has only 5 words associated with it. What are the second characters of these words? E, I, U. So that's why I have E, I, U as the children of B, and so on and so on.
What is the significance of circular and square?
So square here just reflects that it's a leaf node, corresponds to a word. And end of a word, yeah. Okay, clear? Okay, so now how much time, so suppose I had built such a try. How much time does it take to search for a word here? Search for a word. Search for a word. Suppose I give you a word. How much time does it take? Suppose I said bed. How much time does it take to search for bed here? B-E-D. Right? Why? First I come here. Right? So this has 2 children. Okay, how is this organized? How do you think, what kind of a data structure would I have maintained to organize this? A-B tree? No. Okay, this each node can have multiple. It's a multi-way search tree, good, right? But it's not, yeah, it's in some sense a search tree, but each node can have up to 26 children, as I said. So one way of organizing it is that each node has an array of size 26 sitting inside it, right? And the first location of the array points to the node corresponding to A, second to the node corresponding to B, third to the node corresponding to C, and so on. Right? You could organize it, if you organize it as an array, you say you waste space. जैसे यहाँ पर हर एक नोड के 2 या 3 ही चिल्ड्रन हैं, तो आप क्या करेंगे? Instead of an array, you could keep a linked list, right? Ordered according in the alphabetical order. In which case, you know, you will have 2 nodes here. The first node will be pointing to B, and the second node will be pointing to S, right? And you will say that this is B and this is S. Now, given this, how much time does it take to search? So suppose I had linked lists at each nodes. Why would this change the search time? 26 times the length of the pattern that the word I'm searching. Is that clear? No? Yes? It's not clear. Power? Okay, this is a node. Oh, sorry, I wanted to make a, I wanted to make it a linked list. So I have a linked list sitting here. Okay. And in each of the nodes of this linked list, there is a particular character which says कि आप जो word ढूंढ रहे हो, अगर उसका पहला character ये है, तो इसका pointer follow करो. ठीक है? तो हर एक नोड ऑफ द लिंक लिस्ट से एक पॉइंटर जा रहा होगा और यहाँ पे कुछ लिखा होगा. यहाँ पे मान लीजिए B लिखा हुआ है, यहाँ पे D लिखा हुआ है, यहाँ पे N लिखा हुआ है, यहाँ पे X लिखा हुआ है. तो आप जब किसी वर्ड को सर्च करने के लिए जाओगे, मान लीजिए आपका वर्ड S से शुरू होता है, तो you'll have to run through this linked list first to get to S and then follow the pointer. So if S is not there, you can stop right away, but maybe S is there, in which case you'll have to follow the pointer and repeat this thing. So how much time does it take in the worst case? You might have to traverse 26 nodes of the linked list into the length of the word. So 26 times.
So you said using array we will waste space.
Yeah.
If you use a linked list, then you waste some time also.
Yeah, you waste time.
So what is preferred, wasting time or space?
What do you think is preferred, wasting time or wasting space? See, there is no unanimity, as you can imagine. So there is no one answer to this. It depends upon what you have in Ample, right? If you are writing a program where space is at a premium, your system space is at a premium, you would rather waste time. If time is at a premium, you would rather waste space. Right? So it depends upon the particular application you have and what kind of a computer system you are running it
So
on.
when we generally write a program, what should be our efforts to reduce?
Both. Okay? Okay, so now let's look at the operations of find. So find, I said, how much time does find take? Pardon? I'm using, let's say, a linked list representation on each node, right? So 26 is the alphabet size. I'm using D to denote it. Maybe your alphabet was not 26 large. Maybe you had whatever, a smaller alphabet, a larger alphabet, whatever. And M is the size of the string or the word that I'm searching for, right? So that's the time for find. And can you see that this is also the time for insert and for delete? Huh? Yeah, when you are searching, you keep coming down and then you don't find it anymore. If you don't find it anymore, what do you do? In insert, you'll create that letter, put it in the linked list, make a pointer down, and maybe you'll have to create new nodes. Do you want me to show how you would do this? No? Okay, suppose we were trying to insert, let me quickly do it, right? What do I want to insert? Bed. Bed nahi mila tha hame, right? B-E-D is what I want to insert. What will I do? I'll search for bed. I'll come down here, B found. Here I would have seen a B, so I come down here. Then here I would search for an E, I come down here. Here I'm searching for a D. In the linked list here, there's no D, so I create a node. Right? Now it will be a square node because it's the end of the word, and this would have D written in it. That's it. Right? But if I had BEDS, then I would create one circular node and then a square node below. Right? I might have to create such a longer chain here. In any case, total time taken would be proportional to the length of the word.
Sir, if bed is already there and we want beds to be there, then beds is already there.
Okay, so yeah, we will come to that issue later in this class. Yes? So when one of the words is a suffix of or is a prefix of the other, that's what you are worried about. We'll see all of that. Right? So search, find, find, insert, delete. All will take the same time, order DM. But one thing is bad with this data structure, and that's the space requirement of this data structure. How much space does it take? 26 times the number of nodes. How many nodes are there? Huh?
The number of
How many nodes are there in this data structure, in this tree that we have created? Number of letters?
Distinct.
Number of strings? Number of distinct letters?
no sir,
You are saying there would never be more than 26 nodes in the tree then? Length of the longest word.
Total, sir, total number of strings type in the,
Huh?
total number of words or strings in the entire text.
Total number
Total number of characters in the entire text, which is the size of the text.
Worst
That's the
case.
worst case. And it can be close to that worst case. Yes? No. I have, let's say, 10 words. let's say I have 10 words, each beginning with a different character. Can happen? The first word begins with an A, the second with a B, the third with a C, the fourth with a D, and so on and on. And फिर इनके नीचे हम बनाते जाएंगे एक लंबी सी chain, depending upon what the size of this word is. B के नीचे भी इसी तरह बनाते जाएंगे, C के नीचे भी. कितने nodes हो गए अब? As many as
Total number of
the
words.
total, not total number of words,
Letters in the letters in the all the words.
which is exactly total size of the strings in S.
Right.
By size I mean put all their characters together and their total size. Let's call that W, so that's the space requirement. Yeah, which is too large. Okay, so we got to do something about this one. Before that, let's see applications. So this actually does our task, what we started off with, right? So suppose I give you a piece of text and I take all the words in the text and throw them into a trie. I make a trie out of all the words in the text. Now if I have to search for a particular word, yeah, I can search for the word in time proportional to the length of the word. This is what we started off with today, right? So I can do word matching, find the first occurrence of word X in the text. Why have I said first occurrence? Pardon? It will be inserted only once. So one occurrence I can detect by doing that, right? All occurrences भी कर सकते हैं. Okay, we come to all of this in a second. Let me show you an example and you will see that we can actually even do all occurrences. Right? So each of these operations of matching is done by tracing the path corresponding to that word in this trie. So let's look at an example. This is a piece of text. Can you all see the text? No? See a bear sell stock, see a bull buy stock, bid stock, hear the bell stop. Okay? So you have a bunch of words. See, for instance, appears once, twice, twice. So I am looking at all the distinct words that are there in this piece of text, which is see, beer, sell, stock, buy, stock, bull, bid, bell, hear, right? So these are all the words. I throw them into a trie. This is the trie I get. And as you can see, this leaf corresponds to B-E-A-R, bear, right? And bear occurs at position 6 in the text. So with this leaf, I store 6. Okay? Let's look at this, bid. Bid is occurring at two places perhaps, this 47, starting at 47 and starting at 58. So I'll store both 47 and 58 here. This is what we call pre-processing the text, right? I took my initial text and did something, built this trie on it, stored this information with each of the leaves, so that now if you come with queries, where does this particular word appear, I can quickly, how much time do I need? Very little, right? Just proportional to the length of the word, and I'll be able to tell you all the places where this word is in by looking at this number down here, the numbers down here, yeah? Right? Okay. Yeah.
But in all these cases, we are making a try of the words.
Of the words, good, yeah?
We are not making of each and every pattern that exists.
Good. Yeah. So this doesn't really solve the problem that we were talking of in the last class, which was that I give you a piece of text and I give you a pattern and find where all that pattern appears in the text, right? Because my text need not be a collection of words. As I said, you know, my text could be, let's say, sequence of bases in a gene database, right? So I have these, so I have just a long sequence of A, C, T, G, that kind of a thing, and I'm searching for a particular sequence in there. Now what is my word? There's no notion of a word anymore.
But if we could solve that, pattern which we are giving,
Yeah.
if that doesn't contain spaces, like in breaks in between words,
Right.
if it doesn't contain,
Right.
then we can automatically, I mean, when we put the pattern,
Yeah.
if we encounter a null string, null pointer after that, we can stop our search and check either the end case would be when the pattern doesn't correspond, or otherwise when we get the end and we get that the pattern is still matching, then we can say the pattern has been found.
But how will pre-process the text? When there is no notion of a word, how will you pre-process the text?
No, he's saying we can define some character to behave like a space, but that's not correct either, right? Because then again there is no notion of a word, right? It could span many places.
But the
special character like space or comma, we can again start searching for that. We also we have a part of the.
No, so here we have a notion of separate notion of words, and if we are searching for words, that's okay. Suppose I was searching for AR blank SE, right? Then I cannot search for that in here.
the blank would create a problem.
See, so if I have a pattern like that, so if I don't, if I think of these blanks also as some special, as another character of my alphabet, then I cannot really search for anything like that, right? So the reason I can search here is because there are well-defined boundaries, right? And my pattern has to begin with a boundary and end with a boundary. That's why I can search, right? So we need to do a little bit more, and we'll come to suffix trees, which will help us do that.
We can create a node and we can connect all the leaves to that.
No, it's not straightforward. We'll see all of that. Okay. So now first we'll address the issue of the large size that this trie has. Let's try and reduce the size of this trie first. Okay. So we'll do the following. We are going to look at all nodes of the trie, so which have degree only 1, and remove those nodes. Degree 1, by degree 1 I mean who have only one child, and I am going to compress those nodes. Okay. So if this is my standard trie, see that there are a whole lot of nodes here which have only one child, right? This node, for instance, this node, this node, this node, in fact this node as well as this node, right? This node also has only one child, this has only one child. So I am going to compress them. By compress I mean I am going to take the child and collapse it into the parent, and if the resulting node also has one child, I am again going to take the child and collapse it into the parent and keep doing this, right? तो जो मेरा पिछला एग्जाम्पल था वो अब ठीक हो जाएगा, right? In my previous example I had said I have a trie in which there are a bunch of words, each of which begins with a different character, right? So I had created such a thing, a long chain like this. Now if I compress them into a single thing, then this entire thing becomes just one word, one node here. Yeah, so I'll just show that to you in a second. Oops. This is what my compressed trie would look like, right? Sorry, this is overlapping with this. There is one node here that got missed. So this part is the same, B and S is the same. ID collapses into 1. This becomes ID now. Now a node doesn't have just one single character but a string as its label, right? This EAR collapses here, L collapses there, and so on and on. Okay, as you can see, this is smaller than this, right? Why would this take less space now? Okay, what is the number of nodes in this thing now?
Coefficient decreases.
What is the number of nodes here now? Nodes first, then we'll worry about the labels later. Okay, so this is a fact which you will prove for yourself. It's very simple. Suppose I have a tree which has L leaves in it, and every node of the tree has at least 2 children. Every internal node of the tree has at least 2 children. Then the number of internal nodes cannot be more than L minus 1. A tree in which every node has at least 2 children, by that I mean, except leaf nodes clearly. Leaf nodes don't have any children. Every node has at least 2 children, has at most L minus 1 internal nodes, where L is the number of leaves. If every node has at least 2 children, then the number of internal nodes is not too much. Okay? This is a very simple thing, you can prove it by induction. All of you should be able to do this. I will not prove it today. How are we going to use this? How many leaves are there in my trie? Number of words. This says that the number of internal nodes is going to be the number of words minus 1 at most. So, the number of nodes in a compressed trie is order of S, where S is the size, is the number of words. Capital S was the set of strings, so S is the size of the, this number of words. So, this is the number of nodes in a compressed trie. Now, this does not solve our problem completely. Why? Because each node now has a longer label now inside it. उस label को भी हमें store करना होगा. Yes? उस label को store करने के लिए भी space चाहिए. तो वो कहाँ से आएगी? Okay, we are going to store the labels not as labels but as numbers now. And let's see what I mean by that. Let's look at this label ID, right? This was the last 2 characters of the word BID. Yes? So, BID word bid is the 6th word, let's say, in my collection. I have kept all these words, let's say, in some array, in some arrays. And ID is the last 2 characters. So, in the 6th word, right, ID begins at position 1 and ends at position 2. So, each of these labels, no matter how long they are, can be stored as 3 numbers, because each of these labels will be a substring of one of the words. Do you follow what I mean by substring of one of the words? Yeah? No, not necessarily a suffix or a prefix, although in this example it looks like a suffix, but it not necessarily, right? For instance, TO, no, so TO is not a suffix. It could be, that's what I am saying, substring. I am not saying a prefix or a suffix, I am saying substring. So, what is a substring? And everyone understands a substring of a string. A part of the string, contiguous part of the string is a substring.
But then the space usage again.
Okay, now what is the space used by the trie? Okay, you will have to store these words somewhere, right? This is your input. This is stored somewhere. So, we are just trying to figure out how much additional space we are taking for our data structure then. And how much additional space are we taking? Total number of characters. No, now the space I am taking by this data structure is number of nodes. Number of nodes is number of words, 2 times the number of words at most, into 3 for 3 integers each. वो तो constant है, because then there are some pointers and stuff like that also. They don't? Why is that? Oops, sorry, yeah, this is something else. It's only the BID which corresponded, huh? I'm glad I took the right example. No, I think except for this 703.
E double L, exactly.
Also ELL, huh?
And 011 is not ELL.
I'm sorry. So, this should not be, so what is ELL? ELL should be 213.
213.
Right, there is a problem here, sorry. TO2, is TO2 312? 312 is okay, yeah, sorry. Yeah, so there are some problems, but there are a few okay things also. Let's look at the positive side.
So, if we have a multiple character, I mean the character occurs multiply, like we have S, it occurs in C, it occurs
Yeah,
in
so you can place take any one position, right? It doesn't really matter, because when you are searching now, when you come here and search, what does it mean? Right, you will take your, let's say the first character was a B, yeah, so you will follow the pointer of B. Okay, now how does searching happen here? Let's look at that.
We'll have to correspond back to the text number.
We'll have to go back to the text and see. Yeah, but those are sitting in arrays, so you can access it in constant time.
Right, take the first, we make a 2-dimensional array, take the first put in that, and the other two can be the other index. Take a two-dimensional array in characters.
Yeah, there could be many ways of organizing this. You understand the general idea. Okay, now how does insertion and deletion happen in a compressed trie? Suppose this is the trie I have. So the labels that I had put at a node, you can also think of them that they are the labels on the edge, the parent edge of that node, right? It's one and the same thing. You understand what I mean? पहले हमने यहाँ लिख रखे थे इस लेबल को A यहाँ लिखा था, अब हम इस लेबल को इसकी इस एज पे भी लिख सकते हैं. कभी हम यहाँ लिखेंगे, कभी हम नोड के अंदर लिखेंगे. अगर हमारे पास नोड के अंदर जगह नहीं होगी तो हम ऊपर लिख देंगे. ठीक है? तो यहाँ पर ये B इस तरह से है. Now there is also a subtle reason why I am doing it this way here, right? And you will see why. Now I am searching for this string BB. I start searching, right? So conceptually it is the same as saying I see a B here, I come down. Then the first here is an A, this is a B, so I should go this way, I come down here. Now the third character I have is an A. Yes, so I am looking for an A. The first character here is an A, the first character here is a B, so I should come down here. And then I start matching this with the label here. तो मेरे पास AAB है, यहाँ पे है AAA. तो ये B पे गड़बड़ हुआ, इस वाले B पे. तो मैं इस एज को तोड़ दूंगा. ठीक है? ऊपर वाले पे क्या लेबल जाएगा? डबल ए. ठीक है? यहां पे एक नोड आ जाएगा. उसका एक चाइल्ड पे क्या आएगा? ए, और एक चाइल्ड पे बीबी. ठीक है? कुछ we are not doing anything sophisticated. You should now get familiar with these things, right? We are searching for this pattern. We are moving down the tree. जहां तक मैच किया और जहां नहीं मैच किया वहां एक नोड डाल के एक खींच दिया दूसरा, right? एक एज खींच दिया. So degree is number of children. Number of children is at least 2, right? अगर number of child 1 था तो we compressed it into the parent, right? So we are searching for BB, we are inserting BB, AA, BB, which means we first search for it. We search for it, we reach the middle of this edge, so to say. That's what I'm trying to say, right? Till the middle of this edge, we have matched B, B, A, A. पर हमारा next character B है और यहाँ पे next character A आ रहा है. तो हम इस edge को break कर देंगे. यहाँ एक node डाल देंगे. ये red node is the node I have inserted. एक तरफ इसका child A हो जाएगा और ये वाला नोड हो जाएगा उसके नीचे और दूसरी तरफ हमारा BB हो जाएगा उसका. That's all. This is how you'll insert. Now how will you delete? Same. What do you mean by same? We proceed, we find the node, we delete. Now something else has to be done.
Combined with the parent.
Yeah. If the parent, so suppose I were to delete BB, AA, BB, I'll come here, I'll delete this guy. Now I'll look at the parent. If the parent has only one child left now, then collapse the child with the parent, and you might have to do this multiple times. Yeah, so that's all. Very simple data structure, right? I'm leaving out the implementation details. You'll have to figure, some things. अगर आप array से कर रहे हैं, linked list से कर रहे हैं, कहाँ क्या करना पड़ेगा, कौन सा pointer move करना पड़ेगा, that you'll also be able to figure out by now.
Why would we do multiple times? Because वो पहले ही हो जाता था.
Multiple times नहीं करना पड़ेगा. I think you are right. एक ही बार करना होगा. Okay. Now tries are very useful. Okay. They are used in web search, right? Because you can imagine why. You go into Google, you type a word, and it retrieves to you all the web pages that have that word. Yes. So the index, that part which helps you retrieve all the thing is called the index of the search engine. So it is stored as a compressed trie typically, right? I'm not saying that Google does it this way, but this is what a generic search engine would do. And each leaf of the trie is associated with a word, and together with the word, जैसे हमने वहाँ पे word के साथ occurrences डाले थे उसके text में, now we will have कि कौन कौन से URLs हैं जिसमें वो word occur करता है. Right? That's called the occurrence list. The trie is kept in internal memory. The list can be very, very long. If you type a word like computer, imagine the number of URLs, pages that would contain that word. So this occurrence list would be huge, right? So that's why it's not kept in main memory. It's kept on disk. Okay. Now suppose you wrote computer and what? Huh? What is something, right? Music. Let's say music, right? So now what does this thing have to do? It will search for computer, it will search for music. It will get two occurrence lists. Now it has to take their intersection. So Boolean queries correspond to set operations on these occurrence lists, right? अगर आपने and दिया हो तो intersection और दिया हो तो union, right? Of course, there are lots and lots of techniques that go in to speed up the thing, right? You eliminate stop words, many other things. We will not go into that, right? They are also used in internet routers. Okay. Now you are all perhaps familiar that each node, each computer on an internet has a internet address, an IP address in internet protocol. It's a 32-bit number, right? And it's written in this kind of a notation. So google.com, I just checked, is something like this, right? Now what happens at a router? So you can use, let's say there's a utility called NSLOOKUP in Unix to find out the IP address of any node that you want to. Yeah. So a particular organization just uses uses addresses which are all related in a certain manner, right? So for instance, although this is a private address, is not such a great example, but all IT Delhi addresses, all internal addresses of ours will look something like 10 dot something. Okay. Now how is routing done? In a router, right, when packet comes in, it has an IP address written to it, right? अब राउटर के अंदर एक टेबल होती है which says, which doesn't say कि अगर ये IP address है तो उसको आप यहाँ भेजो. राउटर क्या है? A router is bunch of links coming in, links going out. So a packet comes on one of the links and the router has to figure out which link to send it out to, right? So the routing table does not say कि अगर ये IP address है तो इस link पे जाओ, क्योंकि IP address तो बहुत सारे हो गए, 2 to the 32 different IP addresses हो गए potentially. वो तो बहुत बड़ी टेबल हो जाएगी, तो वो ऐसे काम नहीं करता है. वो ये कहता है कि take the IP address of the packet and find out the longest match, right? तो आपके टेबल में लिखा होगा, your table would have कि anything that begins with a 10 यहाँ भेज दो, anything that begins with a 10.27 उसको यहाँ भेज दो, anything that begins with a 10.27.36 उसको यहाँ भेज दो. So now what is the router going to do? It's going to find out the best possible match of these three.
Searches for all occurrences and then takes the longest. I mean, if it doesn't see a 10 and go through, it first searches if there is a bigger.
Right,
match.
it will try to find out the longest match. Okay. So if the packet had 10.27.36, then it will go on the 36 wala route. But if it was 10.27.34, it will take the 10.27 wala route. And if it was 10.28, it will take the 10 wala route. ठीक है? तो इस तरह से routing tables organized होती हैं. So there also tries are used to do this. So or tries could be one way of doing it. So we'll come back to pattern matching now, right? So we saw compressed tries are doing the job reasonably well, provided there was a notion of words or whatever delimiters, and our pattern started and ended at a delimiter. Yeah, but suppose you are, as I gave you an example, if you are searching in a biology database, there is no notion of a delimiter there, right? What do you do then? So this is something we said before. Instead of pre-processing the pattern, we are going to be pre-processing the text. And now what we are going to do is the notion of what's called a suffix tree. All suffixes of the text, everyone remembers what a suffix is, right? Prefix, suffix, substring. Suffix is last one. So you'll take all suffixes of the text and organize them into a tree. Okay, and you will see what I'm trying to say in a second. Okay, this is let's say a piece of text XAB XAC, right? How many suffixes does it have? जितना बड़ा टेक्स्ट है उतने ही हो जाएंगे, 6 suffixes हो जाएंगे, right? I'm not saying proper suffixes, I'm saying suffixes, all, right? Now I'm going to take them as my words. XAB XAC is one word, AB XAC is another, BXAC is another, XAC is a fourth, AC is a fifth, and C is a sixth. These are 6 words, and I'm going to create a trie of these words, in particular a compressed trie, and this is what the structure is. And this is what I have written here, you can ignore. It is exactly the definition of a trie. Okay, so let's see why it's a trie. Here, if it were a B, I would go this way. If it were a C, I would go this way. If it were an A, I would go this way. If it were an X, I would go this way. Yes? X से जो भी begin हो रहे हैं उनमें next character A आ रहा है, तो X का एक ही node होगा, child node A, तो इसलिए X और A combine हो गए. पर X A से जो begin हो रहे हैं इनका next character या तो B है या C है, तो C में एक possibility हो गई और B में दूसरी हो गई. ये जो numbers लिखे हुए ये क्या है? Numbers, the starting position of that suffix. So this corresponds to SA, XA, B, XAC. What is the starting position? 1. This corresponds to XAC. Starting position 4. This corresponds to AB, XAC. Starting position 2. AC, starting position 5, and so on and so forth. ठीक है? सारे सफिक्सेस हमने एक ट्राई में डाल दिए, तो इसलिए हम इसको सफिक्स ट्री कहते हैं. सफिक्स ट्राई भी कह सकते हैं, ठीक है, पर हम सफिक्स ट्री कह रहे हैं इसको. So it's essentially a compressed trie for all the suffixes of the text. So it seems it would be huge, right? But why should it be huge?
Length of text.
So how many suffixes are there? As many as length of text. So we'll have that many words. Recall that the size of the trie is just the number of words, order number of the words. So it's just order length of the text. Right? नहीं समझ में आया? कितने वर्ड्स हैं हमारे इस ट्राई में? जितने साइज ऑफ द टेक्स्ट है हमारा, ठीक है, और जितने नंबर ऑफ वर्ड्स होते हैं उतने ही इंटरनल नोड्स होते हैं, ज्यादा से ज्यादा आपके ट्राई में उतने ही टोटल नोड्स होते हैं, 2 times that number. So the size of the trie is not too much. So suffix tree for a text X of size n from an alphabet of size D stores all the n suffixes of X in order n. D लिख सकता हूं मैं यहाँ, D constant assume कर रहा हूं, तो order n space में लिखा है, ठीक है. D is typically small, right? So it doesn't require too much space.
Sir, but वो तो पूरे document अगर if we have a document, तो अगर if we store the suffixes पूरे document को एक मान के अगर तब then it will take order time. But for every word there may exist.
नहीं, तो हम हर वर्ड के लिए सफिक्सेस नहीं बनाएंगे, हम पूरे डॉक्यूमेंट के सफिक्सेस देखेंगे.
But what purpose will it solve? क्योंकि अगर हम किसी सर्च कर रहे हैं,
हाँ,
तो it need not be कि मतलब हम suffix आगे वाला portion दे, बीच से पूरा portion उठा के हम देते हैं.
Maximum.
we'll come to that. Why are we doing suffixes, right? Can someone think of why suffixes? ये क्यों हम suffixes क्यों डाल रहे
While
हैं?
searching for words, the main problem was the first initial delimiter, not
Right.
the last delimiter, because
Right.
last delimiter can be done with maximum matching.
Right.
So with this we are having that the initial delimiter is not a space or something.
Good.
That's
Roughly you are right. देखिए अगर हम यहाँ पे if I was searching for AB, yeah, what will happen if I'm searching for AB? Suppose I start searching for AB here. Huh? I'll come at A here, and then I'll come at B here, and I'll stop in the middle. But can I say something now? I did not find. That's what you will be tempted to say.
We found it at
We found it.
second and the third position. The second se start, the pattern starts.
Right? So basically, देखिए that means since there is a suffix, whose prefix is AB. देखिए, if the pattern appears in the text, then there is some suffix whose prefix is that pattern, right? So that means that there is some word in the collection of words that I have thrown in whose prefix is that pattern. So which means that when I am searching for that pattern, that word, initial part of that word will match up. Yeah? And I will be able to do something with that. Many of you can see what I will be able to do with that. I will just look at the children of that, the leaves of that subtree, and identify. We'll come to all of that. That's the remaining of this lecture. Okay, so let's say I had this word minimize. So I don't make the suffix tree for each word in the text. I make a suffix tree for the entire text. Remember that, right? So if this is my entire text, I make a suffix tree for it. Yeah. So this would be my. These are all my suffixes. They would be 8 suffixes: 1, 2, 3, 4, 5, 6, 7, 8, and this would be the corresponding suffix tree I would get. Right. Once again, I've collapsed my nodes. Is everyone clear? You can all make this suffix tree. And now we want to do a compact representation once again. How much space do I require? So once again, we instead of storing the labels, देखिए यहाँ बड़े-बड़े labels आ रहे हैं, right? We don't want to store these बड़ा-बड़ा labels, right? So once again, we can store by numbers. Once again, each one of them is a substring. So I just need to know what the start and the end position of the substring is. I don't even need 3 integers now. I just need 2. Because they are all part of one single text, right? So this is, for instance, what would happen. NIMIZE, NIMIZE starts at position 2, ends at position 7. I just write 2, 7. Pardon? Yes? Question? No. Right? So I can store it very efficiently. Now this is the key thing which we are using in pattern matching. So if I have 2 suffixes XAB, XAC, and they have the same prefix XA, so if 2 suffixes have the same prefix, then their corresponding paths are the same at the beginning. And that part is and it's just the concatenation of the edge labels of the mutual part, right? So XAB, XAC, XAB, XAC ये है, XAC ये है, इनका कॉमन पार्ट XA है, तो वो यहाँ पे इस तरह से आएगा. Yeah? This is going to be crucial in a short while, right? Because now if I was searching for XA, ठीक है, तो I would end up here. Now what? Both of them, right? So I have to actually report all occurrences, and this will help me do that. Right? So what do I have to do to report all occurrences? Basically, I have to look at its children, look at the leaves in that subtree, and that will give me the positions. Okay, we'll come to all of that. This was the problem that someone had pointed out very briefly in the beginning. If one word in my trie is contained in another word, is a prefix of the other word, what happens? So the same thing, right? So suppose I have suppose I have a word, my text is XAB, XA. Okay? Yeah? Now what is going to happen? I have one suffix which is XA and another suffix which is XAB, XA. This suffix XA is a prefix of the other suffix, right? So in my trie, what is going to happen? You know, one of the words is going to end up at some internal node. You don't see a big problem with this?
Then it won't know where to stop.
Okay, let me, I don't have a slide on that. Let me quickly show you what I am trying to say. So here इसका जो हम ट्राई बनाएंगे वो कुछ इस तरह का, yeah?
It's a rubber.
Yeah, I thought I picked up pen. राइट इसका हमने बनाया एक्स ए और फिर बी एक्स ए यहां पे आ गया, ठीक है। इसका एक सफिक्स है एक्स ए, एक सफिक्स एक्स ए बी एक्स ए है। ऑफ कोर्स बाकी सफिक्स हैं ए बी एक्स ए, उनको भी हम इग्नोर कर रहे हैं, ए बी एक्स ए, बी एक्स ए एंड ए। तो मतलब बाकी का ट्री हमारा होगा एक्चुअली ए इसके लिए, बी एक्स ए यहां होगा और इसके लिए होगा बी एक्स ए, ठीक है। यहां पे भी प्रॉब्लम है, प्रॉब्लम इन द सेंस प्रॉब्लम नहीं है रियली, पर हम अभी तक कह रहे थे कि लीव्स होते हैं हमारे करस्पॉन्डिंग, हम यहां पे लीव्स पे लोकेशन नंबर्स वगैरह सब लिखते थे। अब या तो हर नोड पे लिखना पड़ेगा क्योंकि दिस इज ऑल्सो करस्पॉन्डिंग टू अ सफिक्स, या तो ऐसे करें, या एक तरीका ये है कि हम हर एक के एंड में एक स्पेशल कैरेक्टर डॉलर डाल दें। स्पेशल कैरेक्टर, व्हाट इज स्पेशल अबाउट डॉलर? There is nothing special about dollar. It can well be a, It just is a character which is not part of your original alphabet. That's all. ठीक है, तो अब इस डॉलर से क्या होगा? अब हमारा डॉलर, ये लेबल डॉलर करके ये एक लीफ बन जाएगा, ठीक है, एक से डॉलर। ऐसे ये बी एक्स से डॉलर यहां आ जाएगा, ये बी एक्स से डॉलर ये हो जाएगा, ये डॉलर करके एक अलग बन जाएगा और ये बी एक्स से डॉलर हो जाएगा। अब हर एक लीफ एक सफिक्स को करस्पॉन्ड करती है, ठीक है। तो थोड़ा सा नाइस हो गया आपका स्ट्रक्चर, बस और कुछ नहीं। ग्रेट। सो नाउ हाउ डज वन बिल्ड अ सफिक्स ट्री? सो वी डोंट हैव टू मच टाइम लेफ्ट। So let me, so we start with one suffix. Let's say this is the entire text, right? So that basically is one edge, and then we keep breaking this edge, right? So we'll search for the next suffix. जहाँ तक मैच हुआ, फिर हमने एक बीच में नोट डाल दिया और एक, जैसे हमने पहले ट्राई में किया था वैसे ही हम करते जाएंगे, right? So starting at the root, find the longest path from the root whose label matches a prefix of si through n. At some point no further matches are possible. If this point is at a node, then we denote this by w. If it is in the middle of an edge, we insert a new node and then call this node w, and we create an edge running from w to that suffix that we create. So I can take an example quickly. xab xac है, इसका हमें बनाना है, तो पहले हमने बनाया एक edge xab xac पूरा, ठीक है। अब दूसरा सफिक्स हमारा है ab xac। अब a तो शुरू से ही मैच करना इसने नहीं किया, तो ab xac का अलग आ जाएगा एकदम, ठीक है। तीसरा आया b xac भी इससे मैच नहीं करता, तो वो भी अलग आ गया एकदम। थर्ड है xac, वो xa में जब हम यहां जाएंगे यहां तक मैच करेगा, तो हम यहां पे बीच में एक नोट डाल देंगे w, ये हमारा नोट w होगा, इससे हम xac है तो ये हमने एक अलग कर दिया, ठीक है। इस तरह से आप बिल्ड करते जाएंगे। कितना टाइम लग रहा है इसमें? टोटल टाइम कितना लग रहा है?
Maximum length of the word into length of the pattern, length of the text.
मैक्सिमम लेंथ ऑफ द वर्ड नहीं, देखिए वर्ड कुछ नहीं है यहाँ पे, एक टेक्स्ट है जिसका साइज n है, लेट्स से, कितना टाइम लग रहा है? n स्क्वायर, वाई n स्क्वायर। देखिए आपके पास n वर्ड्स हैं, हर एक की लेंथ जो है 1 2 3 अप टू n है, तो i लेंथ का जो वर्ड है उसको इंसर्ट करने में रफली हमने कहा ऑर्डर i टाइम लगेगा, तो समेशन स्क्वायर। सो दिस विल टेक टाइम प्रोपोर्शनल टू द लेंथ ऑफ द टेक्स्ट। If the length of my text was n, then it takes time order n square. ठीक है? So it is more, it's a bit more, but we'll see what we can do about this one. Okay, so this is the key idea that we are exploiting in pattern matching. So given a pattern P and a text T, our aim is to find all occurrences of pattern P in the text. So the idea of the algorithm is that every occurrence of P in T is a prefix of a suffix of T. अगर P आपका पैटर्न P टेक्स्ट में अकर करता है, तो कोई एक ऐसा सफिक्स है उस टेक्स्ट का जिसका पैटर्न P एक प्रीफिक्स है, ठीक है। सो thus an occurrence of P can be obtained as a concatenation of the labels of edges along the path. So ये थोड़ा सा sentence में गड़बड़ हो गया. Obtained as a concatenation of the labels of the edges of the path beginning at the root. So we can come down the thing and the concatenation of that will give us the thing. So how do we do pattern matching? We build a suffix tree for the text, match the characters of the pattern along the path beginning at the root until the pattern is exhausted, right? So if the pattern is exhausted completely, then that means that we have found a match. If no more matches are possible, then that means that the pattern does not exist. So in case 2, in this case, P does not appear anywhere in the text. In case 1, P is a prefix of a suffix, of a certain suffix which is obtained by extending the path until we reach a leaf. So all the leaves that we can reach, each extension of this suffix, each extension gives a suffix, right? So all the leaves that we can reach from there will tell us the occurrences of the pattern. Each extension provides an occurrence of P in T. So what are the extensions? Basically all the leaves below that. नहीं समझ में आ रहा है?
But all leaves just to, sir, only leaves or लेकिन इसके जगह जो भी part है that will be the remaining document.
नहीं, that will tell you the occurrences उस pattern का ना, जो leaves हैं. Because the leaves में हमने क्या number डाल रखा है? What is the starting position of that prefix? Great. So let's quickly see. हमारे पास ये है एक पैटर्न AW, टेक्स्ट है ये AW, YAW, ब्ला ब्ला ब्ला. ठीक है, हमने AW यहां तक हमारा मैच किया. ये हमारा ट्राई है, ये XZ है, ये X ये है, ये है. ठीक है, this corresponds to this suffix, this corresponds to this suffix, this corresponds to this suffix. यहां पे हमने क्या नंबर लिख रखे होंगे? यहां पे क्या नंबर लिखा होगा anyone? Starting position of this suffix, just the starting position of this suffix, right? So whatever this is, 4, 5, 6, 7. So यहाँ पे हमने 7 लिख रखा होगा, यहाँ पे हमने 4 लिख रखा होगा, यहाँ पे इस पे हमने 1 लिख रखा होगा. So जब हम AW करके हमने यहाँ मैच किया, तो हम इन लीव्स पे जाके इनके नंबर्स पढ़ लेंगे. दैट विल टेल अस कि कहाँ कहाँ ये पैटर्न अपीयर होता है टेक्स्ट में. Okay, so we saw only an order n square algorithm for constructing a suffix tree. It can actually be done in order n time, but that's a fairly complicated algorithm. We're not going to be doing it in this class. Okay, so what is that gives us the complexity, the total complexity of pattern matching. So pre-processing, which means building the suffix tree, we said can be done in order n time, proportional to the size of the text. Although we saw only an n square algorithm today. Yeah, and searching के लिए I have said size of the pattern plus k, number of occurrences of the pattern in this. Okay, this is completely essential. If a pattern is only 3 characters long but occurs 1000 times in the text and you have to say all the times it appears, then clearly you are going to take time proportional to the, मतलब आपको output करने में ही उतना time लग जाएगा, right? Proportional to 1000. So this is clearly a requirement. And why is this coming up? Anyone? Going to the children, right? हमने इतना part यहाँ तक root से यहाँ तक आने में time spend किया proportional to the length of the pattern. But now we have to report all the children of this node. All the leaves, sorry. All the leaves of this node have to be reported. If there are k leaves, we have to go and report all the k leaves. अगर यहाँ k leaves हैं तो internal nodes इस साले subtree में कितने होंगे? k minus 1. तो इस पूरे subtree का size कितना हो गया? k, order k. तो हम एक अगर हमने कोई प्री ऑर्डर ट्रेवर्सल या कोई भी ट्रेवर्सल करके हम इसकी सारी लीव्स को ऑर्डर के टाइम में रिपोर्ट कर सकते हैं. ठीक है, सो दैट गिव्स अस द टोटल कॉम्प्लेक्सिटी ऑफ पैटर्न मैचिंग. सॉरी, लेट मी गो टू द लास्ट स्लाइड. ये तो फर्स्ट है, राइट? आई हैव टू गो टू द लास्ट स्लाइड. राइट, and the space complexity, the total space we required is just proportional to the size of the text and size of pattern to store the pattern and all that. Okay? So with this we'll end today's lecture. So we looked at a faster in the sense that now we decided to pre-process the text, and to search for a pattern we just need time proportional to the length of the pattern. Yeah.